alaikum wa rahmatullahi wa barakatuh. Today's video is about relationship between translational and rotational quantities. As we know that there are some quantities which plays very much important role in physics, such as displacement, velocity, acceleration, mass, moment of inertia, force, and torque, kinetic energy, momentum, force, impulse, work, and equilibrium. And now we will see the relationship between these quantities. First quantity is displacement. In the translational, it is denoted by d, and displacement is denoted in rotational by theta. And relationship between displacement in rotational and translational is S is equal to r theta. Second quantity is velocity. In the translational, it is defined as v is equal to displacement divided by time. In rotational form, it is denoted by omega is equal to rate of change of displacement divided by time. And its relation between translational and rotational is v is equal to r omega. Next quantity is acceleration. Acceleration is defined as rate of change of displacement, rate of change of velocity. And in rotational form, it is defined as rate of change of angular velocity. There are two relationships between translational and rotational for the acceleration. AT means translational acceleration. Translational acceleration is equal to r alpha, and rotational acceleration is equal to r omega square. Omega is angular velocity, r is radius. Next quantity is mass or moment of inertia. In translational case, we use mass, and in rotational case, we use moment of inertia. These are the same quantities in a sense, but there is a difference between mass and moment of inertia is that mass plays a role in translational, and impulse is the analogous of the mass in the rotational case. Relationship between the mass and moment of inertia is I is equal to summation mr square. Next quantity is force or torque. In the case of translational, we use force, and in the translational case, we use torque. Force is defined as the product of mass and acceleration, and torque is defined as moment of force. One important tips is that when r is appear in a formula by the cross product, you can call it moment. For example, tau is equal to r cross f. Here r is radius, and I call it moment of force. The next quantity is which plays an important role is kinetic energy, which is possessed by a body due to the motion. In the translational case, the kinetic energy is defined as half mv square. In the rotational case, kinetic energy is defined as half I omega square. If I replace m by I and v replaced by omega, then I can get the formula of the rotational kinetic energy from the translational kinetic energy. The next term is moment. Moment is defined in one way is the product of mass and velocity, and the other the term which the moment defines is the quantity of motion. Moment tells us about the quantity of a motion possessed by a body. In the translational form is I have defined it by m is equal to mv, and in the rotational form it is defined by L is equal to I omega. Here m is, if I replace m by I and v is replaced by omega, then I can get the formula of the momentum in the rotational case, and the relationship between the translational and rotational term is L is equal to R cross P. The next term is power. Power is defined as rate of change of work done, but it is also defined as P is equal to F dot V, because P is equal to W by T, and W can be written as F dot D divided by T. D by T is equal to V, and from there I can get the formula of the velocity, and P is equal to F dot V, and same thing as I have above done, that P is equal to, if I replace F by tau and V is replaced by omega, then I can get the formula of the power in the rotational case. And in the rotational case, power is defined as tau, which is moment, torque, and omega, which is the angular velocity. The next term is impulse. Impulse is defined as the product of the force and their time, which is a very short. And in the rotational case, impulse is defined as tau multiplied by delta t. It is the same if I replace f by tau and delta t, it remains same in the rotational case and the translational case. Then the next quantity is force, and is work. Work is defined by F dot D. It is the product of force and displacement, and in the rotational case it is defined as the product of the torque and angular displacement. Simple. Here I also replace F by tau, and D is replaced by delta theta. And the next quantity is equilibrium, which plays the very much important role in the case of the equilibrium. If in the translational case delta F is the summation of the F is equal to 0, then I say that the translational equilibrium has been done. In the rotational case, if the summation of the torque is equal to 0, then the equilibrium we can get by this the situation.